Anoop is an esteemed visionary in the areas of multimodal and embodied AI, neurosymbolic reasoning, generative models, robotics, and non-convex optimization. And he's here at AGI 23 to talk to us about are deep neural networks smarter than second graders? I can't wait to find out. Over to you, Anoop. Thank you.
Yeah, thank you so much, Janet. And hello, everyone. My name is Anoop Cherian, and I'm a research scientist at Mitsubishi Electric Research Labs in Cambridge, Massachusetts. And thank you so much to the organizers for inviting me to give this talk. And so let me get to the slides. I hope you can see the slides. Let me. Looks like it's not there yet.
Yep, we can see them. Thank you.
Oh, you can see the slides?
We could see them. They've gone now.
Okay.
Yeah. They're working there for one moment.
Sure.
Yep.
Okay, you can see them now, right? Okay.
Yes.
Yeah. So before I get to this talk, let me tell you a little bit of where I come from. So I come from Mitsubishi Electric Research Labs, which is corporate Mitsubishi Electric's corporate R&D lab in Cambridge, Massachusetts, which is and our lab is like a few blocks away from MIT. This is a 32-year-old lab, and we have about 60 researchers working in various disciplines, including computer vision, from which I'm coming from, machine learning, signal processing, quantum computing, and robotics, among others. And we do basically fundamental research and applied research and publish in leading journals and conferences, and we solve real-world problems and openly collaborate with universities. And that's pretty much the background of the lab where I come from. And now getting to the talk. So we are going to talk about our deep neural network smarter than second graders. And this is joint work with Guangchuan Peng and Suhas Lohit at Merle, and Kevin Smith and Professor Josh Tenenbaum at MIT. And this is going to be published or kind of presented at CVPR 2023 in about 3 days from now. So let's start from the beginning. So this is the excerpt from the Dartmouth Summer Project on AI from 1956, which I'm pretty sure everyone or almost everyone has seen before. This was expected to be a 2 months and 2 months project, summer project, with about 10 people working on defining AI and coming up with algorithms for algorithms that would think like humans. And one of the things that was in that project report or project proposal was on an attempt will be made to find how to make machines use language from abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. And in the recent times, we have been seeing a lot of interesting things going on in AI and AGI, such as ChatGPT or AlphaGo, which can compete with humans in various games, or image generation tasks like Imagen or DALL-E, for example. We have also seen several papers coming up with architectures that can solve university-level math problems, neural algorithmic inference, for example, coming up with new algorithms for solving standard computer science algorithms, for example, in matrix multiplication, etc., with better efficiency than handcrafted algorithms. We have also seen recently things like Make a Video from Facebook that can generate videos from a text prompt. There are also AI-generated things which have won various awards. For example, these are pictures that won awards at Sony World Photography or Emerging Digital Artists Competition, etc. Or there are also news about AI winning literary awards for best novels and such. This is an experiment that we did ourselves. So we, three of us from Merle, so we gave this prompt, three kids named Suhas Lohit, Quan Chuan Peng, and Anup Cherian jointly solve a puzzle and finish writing a conference paper together. And this is the image that Midjourney generated. And this, we were pretty stunned to see this because it's so realistic, and it has taken into account a lot of interesting things that are implicitly assumed in the prompt. And so this was pretty exciting to us to see. And so this gets us wonder, are we there yet in AI, achieving AI or AGI in general? So this is at the very bottom below left, I've shown an image generated by Midjourney for the prompt. Mickey Mouse goes for a vacation in Potato Land. It generates some images which are interesting and realistic, but this is one image where the potatoes are actually growing above the ground. And so it's are they really there yet? And so that is kind of the question that we sought to demystify in this talk by proposing maybe a line of approach or a line of experimentation to show that maybe that we are not there yet. So to put some context to it and kind of have an idea to go forward with. So let's have this question to start with. So please read the following question and select the correct answer from one of the options and provide the reasoning process. This is the prompt that we give to some of these large language models out there. And the question is this: Brian and William are standing in a line. Brian knows that there are 7 people in front of him. William knows that there is a total of 11 people in the line. If Brian is just in front of William, how many of the people in the line are behind William? And then we have 5 options: 2, 3, 4, 5, and 6. And if you ask, I mean, as adults, it's very easy to solve, and the answer is obviously 2. And if we give this question with this prompt at the very top to say ChatGPT says, if there are 7 people in front of Brian and he's just in front of William, that means William must be in the 8th position. Not really quite there. Since there are a total of 11 people in the line, that means that there are 3 people behind William, and therefore the answer is 3. And ChatGPT did not got this. So if you try this multiple times without saying whether the response from ChatGPT is correct or not, we can actually try it, and every time it produces different answers. So out of 10 trials we did, only 1 of them got ChatGPT correct. So this is one of the problems where in our analysis that ChatGPT got the most number of times wrong. And if you ask the same question to say Bard, Google's Bard, it says the correct answer the correct answer is 3. And then the reasoning goes like this: Brian knows that there are 7 people in front of him. He is 8th in the line. William knows that there is a total of 11 people in the line. So William is a 12th in the line, which is perhaps absurd. If you give another chance to Bard, then Bard comes up with the correct answer, which is A. But then the reasoning is wrong. So Brian knows that there are 7 people in front of him. William knows that there are a total of 11 people in the line. If Brian is just in front of William, then this means that there are 7 people behind William, which is kind of absurd. So it comes up with reason, but the answer is wrong. If it comes up with the answer, but maybe sometimes the reasoning is correct. So it's a mix of things. And now, what if we give the same to a second grader? How does he do that? So I don't know whether you can hear the audio, but let's see.
Brian and William are standing in a line. Brian knows that there are 7 people in front of me. William knows that there are a total of 11 people in the line. If Brian just in front of William, how many people are on the line? Are the line behind William? So there's like 11 people. Okay. And Brian's, sorry. So, going to
So he goes into a thinking mode for quite some time. So, and he wants to make sure that the answer is correct, but he hasn't seen this question or anything about this question before. So it's completely out of the box for him. He finds the right answer. So a second grader can solve this quite effectively. So this brings us to the key questions that we would want to ask. The first question is, how well do state-of-the-art AI models perform on tasks that need broad and general intelligence for their solution? Do they transfer knowledge to solve new problems? How fluid are they in acquiring new skills? And how effective are they in the use of language for algorithmic reasoning? So these are, I would say, very tough questions if you come from computer vision and machine learning standpoint, perhaps, and it's quite daunting to even think of where should we start understanding or answering these questions. And so we debated and discussed this quite a bit to think about where should we start. And one of the more fundamental questions that we thought is important to have an understanding of is, are state-of-the-art deep neural networks capable of emulating the thinking process of even young children? And so that became the premise of this work. And so for this question, we propose this task, which we call SMART, which stands for Simple Multimodal Algorithmic Reasoning Task. The task is to design computational models that have foundational skills to effectively analyze, interpret, and solve simple algorithmic reasoning puzzles and generalize to new problems. To have a pragmatic base or grounding for this task, we propose this dataset called SMART 101, which consists of 101 distinct vision and language children's puzzles. So there have been a lot of work over decades that have proposed IQ tests for challenging AI or analyzing or empirically evaluating AI mechanisms. And so, for example, Clever dataset is looking at spatial reasoning problems with language as the question, describing the context and the question. And then there are Bongard problems, which are pure vision problem. I would not say vision, but then they are kind of diagrammatic problems. There is ARC dataset, which is again looking at reasoning skills by interpreting images and patterns. And then there is more complex tasks such as MindDojo from NeurIPS 2022, where there are things that you can do in the Minecraft sort of a setting to devise methods or tools and etc. for solving problems. But we looked at all these different tasks, and they are either specialized, for example, in Clever, there is spatial reasoning, or they have a huge diversity in the kind of reasoning process that you would want. For example, some of the tasks are perhaps needing some sort of adult's knowledge of the world. Some of them are pretty simple. So there is a huge diversity. So analyzing it over the whole spectrum of age groups is difficult. Or they have limited information on how humans perform on them. Like what would be the performance that humans have on these kind of things? So how do you compare the way humans solve these problems against how machines would solve them? So we don't have any such interpretations in many of these tasks. So that thought brought us to this idea of using math competitions as a basis of our evaluation. And it need not be math competitions, but math competitions was something that was more concrete and available to us. That's why we went with this. But any other competitions or kind of tests that humans or kids have would be a basis for analysis is what we are thinking of. So this is we based our data set on this Math Kangaroo or USA Olympiad, which is an annual math competition for school kids from 1st to 12th grade. And we selected puzzles for our data set from 2012 to 2021 competitions designed for first and second graders, that is in the 6 to 8 age group. These competitions have 3 levels of complexity or difficulty, which is simple, medium, and hard. And we used basically simple category for building our data set, which is, I would say, it's between the first and second grader level, not really in the senior second grade, I would say. So this is some statistics on the data set. We have 200K puzzles, which is a little, so I'll get to that. Why is it 200K in a moment? But there are 101 root puzzles, which are unique puzzles. These 101 puzzles are categorized in eight classes: counting, path tracing, measurement, pattern finding, spatial reasoning, algebra, logic, and arithmetic. This is basically a rough categorization of the puzzles, but rough as in like we see a puzzle, and then what is the first skill that you think you would need to approach that puzzle. So that is this basic skill set that is shown in this figure A. But many of these puzzles, as you would see along, will need a lot of other skills, like for example, counting and spatial reasoning together. So there is a lot of compositionality or broad range of skills that you would need to solve each of these puzzles. So that is shown in figure B, where this compositionality of like counting and spatial reasoning and path tracing and other things. So this is the histogram of that. And some of the puzzles would need an understanding of how to read text from images. And some of the puzzles don't need the image part to do the answering. So this is basically, there is an image, but that image is not necessary to provide the correct answer to the problem. So those are the puzzles that we test these large language models like ChatGPT and GPT-4 and Bard and etc. on, because they don't currently have image interface. So we can only provide text questions, so we use a subset of our data set which has only text or needing only text for the solution for those kind of evaluations. So coming to the data set itself. So this is an example puzzle from the data set. So there is a sparrow jumps on a fence from one post to another. Each jump takes 1 second. He jumps 4 jumps. If he makes 4 jumps ahead and then 1 jump back, then he again makes 4 jumps ahead and 1 jump back, and so on. In how many seconds does Jack get from start to finish? And so in this puzzle, like you need to know how many poles are on the fence from the picture. Where is the sparrow sitting, and where does it need to go? So it needs to have an interpretation of the question. It's the details in the question, like how many jumps it makes, has to be associated with the image, and then come up with an answer and select one of the answers from the 5 options. This is the original math kangaroo puzzle that we start with. And one of the challenges here is that you have just 101 puzzles, and that is just not enough to evaluate any state-of-the-art deep neural network if you want to do some fine-tuning or some other training process on it. So how do we approach? That was one of the biggest challenges. And our idea was to actually programmatically augment these original math kangaroo puzzles in novel ways. For example, this is on the right, you see a programmatically recreated puzzle of the one on the left, where the question is different. Question is different in the sense that things in the question are different, like the name of the bird is changed. You can also change the number of jumps it makes, how many seconds it makes, all these other changes. The options are changed, and most importantly, the image is also changed. So we can, because it's a cartoonish image, we have the capability of writing computer programs that can augment or recreate these images using graphic toolboxes. So this is an example of a programmatically recreated puzzle for the puzzle on the left. And since it's a program that underlies this recreated puzzle, we can actually change the arguments or sample the arguments of that program with various arguments, and create as many new puzzles of that same root puzzle or same original puzzle as we want. And as you can see, there is a lot of variability that you can introduce into these puzzles. And so although all these parameters are changed, the underlying algorithm for solving the puzzle remains the same. So if a neural network has to figure out, or it has to be trained to solve these kind of puzzles, since it's the algorithm that is the invariant part of the entire set of puzzles, you can actually train these, or we hope to train the neural networks on these puzzles. So we programmatically augmented all these 101 puzzles to 2,000 new instances of that puzzle. So that makes a total of 101 times 2,000. It's about 200,000 puzzles in our data set. Since these are programs that underlies these instances or recreated instances, we can actually control the complexity of these programs. So, for example, for the root puzzle on the left, we have 3 different augmentations, and each augmentation is of a different complexity. So you have our generated instance number 1, which is pretty simple. There is nothing much of a clutter in it, but you can actually introduce other shapes and distractors and such inside it, so that the algorithm, I mean, the image or the text, everything looks so complicated. But again, if an algorithm really knows how to solve the generated instance, which is simple, it should also be able to carry over the logic to solve the more complicated puzzle on the extreme right. So that's the idea. But in our analysis for now, because we want to keep everything simple, we are basically looking at the programmatic augmentations of the type of this generated instance 1 that is in the second column. And we reserve more complex puzzles for later evaluations if we have better algorithms to do this. So this is an example. I'll give you a glimpse of some of the puzzles and augmentations that we have in our data set. So this is a path tracing class. This is a very simple puzzle. It's actually, I think, one of the first puzzles in one of these competitions, where you have a bunch of creatures, cats, I think, and there's a bit of a clutter, and you want to see who caught the fish. And it's a very simple puzzle for maybe an early first grader to solve this. But apparently, when we did the analysis, we found that it's extremely hard for current neural networks, especially transformers. And we have programmatic augmentations of this with all sorts of mix of different objects and splines. This is another example from the pattern finding class, where you have to figure out the pattern of objects and find out what is object that is in the missing. How many stars were on the board where the juice was spilled, and you have to find the pattern and then iterate that pattern to figure out how many objects were, how many stars were on. And we can do programmatic augmentation with different shapes of this loop, etc. This is another class, or counting class, where you have in the original puzzle, there is a pattern for these bars, and there are bars which are occluded behind it. So you have to do some occlusion reasoning and spatial reasoning and counting to figure out what is how many white cubes did he use in this whole problem. And so it's like I said, it's, even though it is an accounting class, it is not just counting that you would need to solve this puzzle, but you need much more general skill sets. For example, spatial reasoning and occlusion reasoning and other things, and then pattern finding. So that is where the generality of skill sets needing to solve this puzzle comes from. There's another counting puzzle. It's a different. So this is to illustrate that even though we have one root puzzle for counting, another puzzle could be completely different from what you have seen before. So this is another example of the counting class, where the puzzle is completely different, or the skill set or the kind of approach that you need to make to solve this is completely different from the one that you just saw. And then there is arithmetic class, which is perhaps a little advanced for a second grader, but this is a part of, or this is a problem from the Math Kangaroo, which was designed for second graders. So I hope there is second graders, they believe can solve these kind of puzzles. And then there's this logic class where you need some spatial reasoning skills at the same time, some algebra skills to solve it. where there's a village of 12 houses and has 4 straight roads and 4 circular roads. The map shows 11 houses on each straight road. There are 3 houses on each circular road. There are also 3 houses. Where on the map should the 12th house be put? And then there is another spatial reasoning class where you want to count the number of gray cubes. So Mary had a shape using some white cubes and 14 gray cubes. How many of these gray cubes cannot be seen in the picture? And then you have augmentations of that. And then there is algebra class where you need to have some simple algebra skills to solve it. And measurement class is basically that you have a unit of measurement and you want to count the length of the whole thing by repeating this basic unit that you use to do the measurement. And then there is logic sequence puzzles like this. So this is basically, it's not, even though you select one answer from say A, B, C, D, E options, you essentially need to generate or synthesize a sequence as an answer, not just select a number. So this needs some sequential answering skills to produce a correct answer. So so that's the set of puzzles, or some glimpse of the puzzles that we have in our data set. And the hope was to show that there is a lot of diversity in the type of puzzles that we have in our data set, and it is not just one skill that you would need to solve them, but you need a general set of skills, of basic skills, but general set of skills to solve these puzzles, and which a second grader can potentially solve. Now coming to the learning architecture, so we hope to have some sort of AGI, or a general intelligence model, a single model that can solve all these 101 puzzles and their instances. I won't go much into the details of this learning architecture, but this is based on meta-learning. The idea is that there is, maybe I can use a pointer. The idea is that there is, so our overarching goal with this architecture is that we want to evaluate state-of-the-art deep neural networks, like Bayesian models as well as large language models, to understand how effectively they can be trained or fine-tuned or out of the box taken to solve these puzzles. So the architecture has one is a puzzle image head, and then other is the question image head. These are backbones that we take from outside. For example, the puzzle image head could be a state-of-the-art computer vision model that can interpret images and produce state-of-the-art results on a lot of other tasks. For example, it could be a transformer-based model, or it could be a ResNet-based model, or any other model that is state-of-the-art out there. And puzzle question head is a large language model embedding of the question part of the puzzle. It could be a BERT model, it could be GPT, it could be anything else that you would want to try. And then the features extracted from these heads, these backbone heads, are going into a fusion layer using their own tokenization and other things, and extracting the features, and then these are fused. And then we pass it through some multi-layer perceptrons to kind of fuse them better. And then the output is coming from either a set of heads. So that we assume, in some cases, we assume that there is a specific puzzle head for that particular puzzle. So each puzzle has their own heads. Sometimes if you are looking for extreme generalization, then we don't necessarily need to assume that there's a specific puzzle head, but then it comes from a generic answer head, which produces answer to any question that the system has not seen during training. And we train it using this meta-learning laws. So you sample a set of puzzles and their instances, and then train the laws using either the softmax cost entropy laws or regression laws. And then once the answers are produced, we find the nearest answer from the 5 options and report that as the final answer. One part of this architecture is that we don't take the options as input to this architecture, but hope that the method solves the puzzles completely and come up with an answer which can be selected from the set of answers and options. So one demerit or problem or glitch with that is that you cannot use this idea of answer exclusion to solve the puzzles, but you have to come up with the real answer or solve the puzzle. So this is a bit more stringent requirement for solving the puzzles. Now coming to the experiments and results. So in order to understand this whole generalization abilities, we divided the generalization into 4 different categories. One is this extreme generalization, where you divide these 101 puzzles into 77 for training, 3 for validation, 21 for test. Now, this 21 for test is in no way included in the training set. So it's a sort of like a zero-shot generalization by training on the 77 puzzles and then testing on 21 puzzles, which it has never seen before. There is few shot generalization because extreme generalization, when we did the experiment, seemed quite difficult. So we ameliorated its that requirement and kind of had M shot generalization, where out of these 21 test puzzles, we show 10 examples of those puzzles, 10 instances of those 21 puzzles in our training set. So there is a little bit of idea of what these puzzles are during training. And then there is instance split, which is supervised learning, which is basically you show all the puzzles to the method during training, but then there is a held out set from each of these puzzles. The instances are held out, which are used for testing. And then there is answer generalization, where from this held out set or from the training set, you remove or you don't show one specific answer during training, and that answer is used only during evaluation. And the idea is that if the system has not seen a specific answer during training, can it generalize or produce that answer during testing? We use 2 metrics for evaluation. One is solution accuracy, which is the golden standard, I would say, which is an algorithm should produce a correct answer irrespective of whether it's given choices or not. And the second is the option selection accuracy, which is selecting the correct answer from the 5 options. So in that case, like in some cases, the solution might be, the actual solution accuracy can be 0. For example, in this case here, the model produced an answer of 8, but the correct answer is 9. If 8 is not there in the candidate set, but the closest one is 9, then the method selects 9. So the correct option is selected, but the solution is wrong. So solution accuracy is the bar, and which evaluates whether the system has actually solved problem, and option accuracy is a little weaker. We also experimented with 2 settings. One is classification, where the system has to select one of the like number of options, or there is a softmax output. So if the range of answers to a puzzle is, say, for example, 0 to 255, then the answer, it has to produce a softmax softmax output from one of these options. So that is a classification-based training of the puzzles. And a regression is basically, instead of like a discrete range, you can actually have a continuous range. And so it produces a one-dimensional output, which is kind of rounded to the nearest integer. So and trained, the models are trained using L1 laws. And so when we did this evaluation, one of the important exciting things about this data set is that this is actually, these puzzles are actually from competition, in which nearly 3,000 kids participated. And so we have the performances of the kids from these competitions. And so we collaborated with the Math Kangaroo team, and we got the statistics of how the kids performed. And on average, over the 8 categories of puzzles, on these categories of puzzles, we have nearly 77.1%, which is a second grader performance. If we did not train any of these models, backbone models, but just used random guesses, either greedy selection or uniform selection of the answers, we get nearly 20%, which is selection from one of the 5 options. So before I get to that, so there are 2 numbers in these tables. The first one is the solution accuracy, and the second one is the option selection accuracy. So option selection accuracy is the performance from selecting the 5 options. So if it is random, if you randomly select the 5 options, then the performance is like 20%, which is what we would expect. And these are the performances on the puzzle split, which is the extreme generalization setting. So these puzzles the system has not seen during training, and it is trying to generalize only at test time. We also evaluated the recent CLIP model, which is a vision and language model on these puzzles, and the performance is 24%. And FLAVA is another vision and language foundation model, which was published in CVPR last year, which is again nearly 20%. So the performances on extreme generalization are really poor, I would say, or close to random. We did a few short experiments where some of the instances of these puzzles which were held out during the other phase, the extreme generalization phase, were shown, and we see that there is an improvement in performance. Even if you show only 10 instances from each of these puzzles, there is an improvement of about 6 to 8%, which I think shows that maybe these models have some capability of transferring the knowledge if shown some examples, but still not significantly better than random accuracy. Then we did a lot of supervised experiments, and as one would expect, the performances are much better, like almost double the performance that you would get from generalization experiments. And so on the right, you see a lot of different numbers, and I think the best number is with ResNet 50 plus BERT or ResNet 50 plus GPT-2, where ResNet 50 is the image backbone and GPT or BERT is the language backbone. Then even in a supervised setting, the performance is not really 80 or 80 or 90%. I think it's just still below or close to 50%. We tried different transformers and architectures like spin transformers, cross transformers, vision transformers, etc. The performances were within like 25%, and various language backbones, as well as vision and language backbones using on the supervised setting. And on answer generalization, we found that answer generalization is basically when you have not shown one specific answer during training. And if you look at this from a classification perspective, when you train the neural network for classification, the performance, it's close to zero performance. Whereas if you do a regression, which is like you are not showing the discrete classes during training, but only regressing to the closest answer by a one-dimensional regression curve, then you see that performances are better, like 16.3%, which show that it's kind of clear that regression might be better in that situation, because you can actually produce answers which are an interpolation of the answers that you have seen during training. And coming to the supervised split, and when we compare to first grader and second grader performances, in supervised setting, we see that out of 23 puzzles we evaluated, nearly 6 puzzles in a supervised setting, the neural network model performs better. We also did some correlation analysis on the supervised setting, and we find that first grader is overall 22% or 0.22 in Pearson correlation coefficient. They are good in or nearly positively correlated by about 0.4 on one-step puzzles, but then on two-step or three-step puzzles, where it needs 2 or 3 steps to come to the answer, performances are not significant or not good. These are some evaluations on the different categories. For path tracing, we did not have any puzzles in the test set during that 2020 and 2021 period that we evaluated. But overall, I would say the best performing supervised trained model is inferior to that of the kids, even the first grade kids. We also did some analysis on the generalization. So this is a histogram of the accuracies that the system got over the 101 puzzles. Wherever there is blank, those are puzzles that were not used during evaluation, because they were not from 2020, 2021, which we had the statistics on. And in some puzzles, it actually performs quite well, even in generalization. For example, puzzle number 74, which is this one at the very bottom, where there are some numbers and all these. So there is a number on this side and a number on the other side, and those numbers add up. The numbers on the opposite sides of the cube add up to the same number. So what is the number opposite to say 6? That is kind of the question, and it seems like it comes up with the answer nearly 40% of the time accurately. So there is some generalization that happens to specific puzzles, but not general enough for an AGI sort of a thing. We did some meta-learning ablation study, which I'll skip for now. And we then evaluated the recent large language models on a subset of the puzzles, which, if you recall, I had mentioned in the very beginning that there is about 15% of our puzzles have only language or need only language for getting their answers. And so we took those puzzles and then put it into ChatGPT and other large language model backed models. And so ChatGPT 3.5, which is on the 11 puzzles that we tried, gets about 36.4% accurate, which is significantly better than what we had on our data set. On our backbones, for example, it was 15.1 if we used our ResNet 50 plus BERT or GPT-2, and then fine-tuned. Fine-tuned, not on that, but it's in the puzzle split. So it's extreme generalization, whereas ChatGPT gets 336. So it's almost more than double. So, but then there is still a significant gap from what human performance would be, which is 60.4. So there is a lot of room to improve, is what we gather. And then this is another interesting finding that we had, where we show how many times these large language models were selecting the same answer from 10 trials. And we see that these models are very confident in selecting the wrong answer most of the times. It's something to be brooded on, but that is what we have found, that it selects the wrong answer with confidence. So that brings to the conclusion of this talk. So we asked the question to start with: are deep neural networks smarter than second graders? And our analysis using this simple set of second grader puzzles show that they are not yet, not at least on simple math problems. But then it's curious to think about AI models in general, and then the kind of news that have been coming across, like AI models can pass bar exams, solve university level math problems, etc. So there seems to be something missing or something not right, because if a model can pass university level math problems, why can't they do well on simple second grader puzzles? And I think that is something to be thought through, and I don't have a concrete answer of why that is the case. Maybe one obvious answer is that their training set did not have these problems, but is that the real reason, or is there a more fundamental problem that we have to address? So one of the thoughts is maybe we need a more systematic approach to building AGI, taking inspirations from how humans develop their cognition. Maybe as we have very systematic ways to teach human kids to think and do things, and so maybe a more systematic approach is needed, rather than putting all together into a learning model and make it to learn whatever it learns. So thank you so much, and I would like to thank a lot of my co-authors and others who supported this this work. And before I conclude, so this is an epilogue from Sebastian Brubeck's talk at Harvard on his paper on sparks of intelligence. So he gave this problem to GPT-4, which he was evaluating, and so 7 times 4 plus 8 times 8 is equal to what? And he asks GPT whatever 4, and it says the answer is 120. And then it comes up with a reason. 7 times 4 plus 8 times 8 is, we can use the parentheses to group multiplications, but they are not necessary. 28 plus 64, we perform the multiplication inside the parentheses first, then it comes up with the answer, the 92. Hey, wait, but you started by saying 7 times 4 plus 8 times 8 is 120. And then GPT-4 comes up with the answer. Oh, that was a typo. The correct answer is 92, as shown in the solution. Maybe there is a bit of a spark of intelligence somewhere, if you look at it in isolation, is what I'm thinking here. So thank you so much, and let me know if you have questions.
Thank you, Anoop. That was absolutely fantastic. Great data, great results, great demonstration, and great question at the end. So does anyone in the room have any questions for Anoop? Here we go. This is our first question from a woman.
Oh, I was curious who the child was in your video of the child who was pitted against the AI.
Oh, that's my son.
Well, congratulations. He's obviously brilliant. There's quite a bit of research on the innate intelligence of young children and some discussion on how the education system flattens the intelligence that children are born with as far as creative intelligence. And I'm curious about narrowly defining intelligence or narrowly focusing on an examination of intelligence so much on arithmetic and what kinds of things we may be blinding ourselves towards with using such a narrow metric. I would love to hear your thoughts on what considerations have gone into putting such a priority on arithmetic and math.
Yeah, that's a great question. It's just a start, or I would say a tip of the iceberg, because math puzzles were something that we got access to quickly, and you can evaluate them maybe for their correctness easily as well, like the correct answer quickly. Maybe there is a reasoning that needs to be evaluated as well, and maybe there is a silly, careless mistake that you did along the reasoning process. All those things are there, but then you can easily get to the answer very quickly. Evaluate the answer very quickly. And but we are looking at other evaluations and other ways to do things. For example, if you are giving a child a real world problem of like maybe assembling some things. It could be a real world challenge, or it could be a simulated like a Minecraft challenge, and asking them to create some things. How effectively they do it. And so I think that there is a mix of different skill sets that you would need to solve any sort of puzzle or any sort of problems. And here we are putting things on an arithmetic background. But I think the skill set, or if you come up with an algorithm to kind of choose a skill set and then use that skill set to solve the problems correctly, maybe that kind of an approach or an algorithm's kind of ability to do that, I hope we can generalize that to a lot of other settings where the skill set could be replaced by other skill sets. So those are kind of things that we have been thinking about, and kind of proposing similar things for other tasks and in a more general setting. But then how do you generate the test cases and problem settings in a pragmatic manner? I think that is quite challenging in its own right. So so something we are thinking about, but yeah, maybe along the way.
Thank you very much indeed. I've got 2 questions from Bob Ray on YouTube, and then another one here in the room. Hi, Bob. I'm wondering if you're the same Bob Ray, Robert Ray, who spoke earlier. But anyway, Bob asks, Anoop, did any problems in the training set include specification of the steps involved in solving the problem? And let's answer that one first, and then I'll ask the second one.
Okay, not really, I would think. Although there are, in some cases, the problem setting of a puzzle is quite constrained. For example, maybe the numbers are for a puzzle are from 1 to 10. So if you randomly sample these puzzles from the answer range of 1 to 10, maybe there could be repetitions. And we have tried our best to avoid such cases so that the training and test sets are entirely different. But there could be issues that way. But yeah, that's minimal is what we hope. But yeah, so the data set is out there, and it's ready for public to evaluate. So if you find such issues, then please let us know.
Thank you very much. And then next from Bob, he says, it seems like we're asking the model to solve the problem without any intermediate steps. For the ChatGPT versions, did you explore chain of thought prompting?
Yes, we did. So for all the ChatGPT questions, or we posted to ChatGPT, the prompt was that it has to come up with a reason to solve the reasoning process in finding the solution. Like I showed in my some of my previous slides early on, some of these answers or the reasoning process is correct, but then it finally selects the wrong answer. So I think there is a mismatch in the way it selects the answer from how it does the reasoning. But in our case, we don't have a reasoning as such, because our training is entirely within the problem setting defined by the Smart 101, and we don't have access to a reasoning process from the kids who solve these puzzles. So currently we don't have that, so we cannot really produce it. And we can only produce the final answer. But we'd like to have some reasoning if some data is available on that.
Oh, okay. Thank you for that. It's fascinating. So I can only speak to the logic problems, but why exactly are we doing AI that goes back 50 years? So my wife's an educational psychologist, worked in the schools with the type of kids that we saw. That's a gifted kid, clearly. Why are we doing it? And why are people who are seemingly intelligent writing papers where they talk about the sparks of AGI when the system is absolutely abysmal? Okay, 2 more years, that kid can prove the answer. Forget about getting the answer correct 100% of the time. Prove it when the teacher says, well, why? So maybe you can explain. I'm totally dumbfounded. Ben said he's old. No, I'm old. 64, right? So this is insanity. How does somebody get paid to go up on stage and talk about sparks of AGI and show an example in which a simple problem of the type that you showed at the? Can you explain this? Because I don't get it. I'm totally mystified, right?
Yeah, I agree. I mean, I think this is it's hard to understand. So the idea, I think, is that there is a lot going on in that trillion-dimensional space. Potentially, maybe similar, or we don't really understand what is going on in there. And the thought is that maybe in that space, it's a lot of I don't know. Maybe some weird things going on, which is creating this. So there are a lot of interesting ideas or interesting things that paper showcases in the Sparks of Intelligence paper showcases, and it's brilliant. But then there are simple things, which is also what we see in our data on our data set that are going wrong. And I don't know, it needs a bit more understanding of what is happening in these large language models and what we are missing out. I think that's kind of the curious question that we all have as well. And we don't have access to these large language models like ChatGPT and such, so we don't really know how to analyze it or understand it. But yeah, those are kind of the things that I think we should address going forward.
Okay, well, thank you very much indeed, Anup. We seem to be out of questions in the room, and we're also, oh, you have one more.
So, I've been listening to all these cognitive scientists and, all these blue sky stuff, but I'm a computer engineer. I build computers to solve problems, okay? And so far, people have been working on program synthesis, for example, for almost 50 years now, with almost no consequential results. So if you look at it from a purely computation point of view of, they were curating, language models, they were curating, there was computational linguistics, there were all these spheres where people were making they're putting in an enormous amount of effort with almost no payoff. And here you have a model which has zero human input, okay? So all it's doing is it's just taking these billions of tokens, trillions of tokens, and it's just pre-trained this thing on these tokens. And it's actually generating a Java program that is correct. I mean, isn't that mind-boggling? I mean, it's kind of like, it is sort of complaining about the peanuts that you're served on an airplane when you're actually flying 30,000 feet in the air. So rather than looking at the 30,000 feet, you're complaining about the peanuts. You know what I'm saying? So this is spectacular. It's amazing from a computational point of view, but the cognitive scientists, I don't think they understand computation well enough to be able to comment on this thing, okay? So I think it is amazing. It's incredible. It is mind-boggling. It is revolutionary. Okay, it can do a few math problems. Big deal, right? I mean, who cares, right? So someone said that yesterday, right? Academics is, what is it? Pointless or something like that, right? I mean, all these are academic exercises. They mean nothing. They really have no consequence at all in terms of engineering. Thank you.
Thanks.
How long is it? You can have 90 seconds. Can you rejoin in 90 seconds?
I hope it will be very short. Computer science as the basis for the reply. We have a hierarchy of problems, many hierarchies in computer science. These problems don't even make it into the hierarchies. These are algorithmically solvable problems with single algorithms, which in the polynomial hierarchy are absurdly easy. We also have the arithmetic hierarchy, okay? These problems are all solvable. The arithmetic hierarchy starts with problems that are further on. If we want to abandon the entire basis that we built for what computer science addresses and how hard their problems are, fine. You conveniently leave out the fact that if you want to verify a program of any complexity in the real world is correct, it's Turing unsolvable. And it's incredibly difficult. So if we want to just call these things for alchemically based programs and run them, fine. I want no part of that. I want a program that I know for anything that's high stakes works. And if we want to do that, it ain't going to be this technology. It's going to be some marriage of it, as we saw in the first talk, I think, today, with something that's more rigorous. Thank you.
Thank you.
Thanks.
Yeah. Oh, we need to get you.
Rejoined her. I mean, I agree with Summer regarding AGI, and I mean, as Noah pointed out, also, I mean, there are real computational limitations to what transformers are doing, which can be worked around only in hacky ways that clearly can't be the answer to AGI. And I mean, in my own work on AI with OpenGOG, Hyperon, and Meta, I mean, we're trying to make something that can deal with all sorts of complex logic systems and whatnot, and grapple with these more advanced problems. On the other hand, we're not yet showing results like these results, right? And so, to take a much simpler example problem that we'll talk about in the NLP workshop on Monday, I mean, I spent many years, working off and on along with other projects on the problem of translating English sentences into, say, higher order predicate logic expressions that will roughly capture the meaning of those English sentences, right? And not necessarily fully capture it, which is a complicated thing, but capture enough of it, you could do a lot of interesting reasoning. And even in the domain like biology, like PubMed abstracts, which is pretty cut and dried, referring to some specific physical reality. And it was hard. I mean, we trained neural nets supervised learning wise. We made rule-based systems. We had combined systems, and it worked okay, but you're like eking out extra percentage points here and there. I mean, now playing with fine tuning and few shot learning on GPT-4 and Llama and other systems, we don't yet have the problem solved as well as we'd like, but we're getting just vastly better results at mapping ordinary natural language English, either common sense, blah, 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 or PubMed or whatever it is, into predicate logic expressions. And you can tweak it to do higher order predicate logic, first order logic, paraconsistent logic. So this problem restricted to sentences of the length that you see in regular human discourse. I mean, this is not necessarily high up in the formal computer science hierarchy, right? Because I'm not going to say transformers could solve this as n goes to infinity with really long sentences in some way. They can solve it for the sentences on the internet, which is indeed what they were trained on. But the thing is, a very high percent, in my own view, which isn't proven and may disagree with yours, in my own view, a very high percent of what I do every day, and I'm a fairly clever guy, is not that high up in these computational hierarchies. Like, I just do a lot of simple stuff every day, and a lot of that simple stuff does seem to be done adequately by these transformers. Like, an ethical judgment is one example. Like, I did a bunch of trials myself, just like give paragraphs posing everyday ethical conundra to a transformer, and then ask it, like, what would a benevolent, open-hearted, wise person say about this? You know, it gets it right as much as a person. Now, there's loads of examples like that online, but I mean, a year ago, I had no system that could do that, right? And trying to make a system that could do it would have been quite painful and tedious with rules or supervised learning. So, I mean, I do think, I mean, I'm blathering on so long because this is sort of like this is really the key conundrum we see in so many talks at this conference, just given where the AGI field is right now. I mean, I think almost everyone in this room knows you're not going to get a human level AGI by taking transformers and adding a few little things onto them and improving them a little bit. I don't know that any of us really knows what nature of powerful system with what exact kind of power you could get by doing that, though, because of course, a pocket calculator or Google is already smarter than humans in some dimensions of intelligence. So in what dimensions of intelligence could you actually get a transformer to be how good by, even if it's not a human level AGI? We don't know that yet. And I don't feel like I know what percentage of a real AGI, a human level AGI system, a transformer neural net could be. Like I mean, my friend Gary Marcus thinks the answer is probably like half of 1% or something. And of course, folks at OpenAI may think the answer is 90%. My current gut feel is around 20%, but we really don't know. And I mean, it's fascinating research topic. So, I mean, I think it is important to flesh out exactly what they can do and can't do. But I mean, it's also important to do as Selmer has done and say, well, there is this stuff, like people in this room can do that. There's not any reasonably plausible path to get transformers to do that just by tweaking with them a bit, or which is my view, which not everyone's going to agree with either. Yeah, go for it.
Thank you.
GPT-4 gets 100% of the Winograd challenge questions correct. And humans sometimes only get 90%.
Well, I'm wondering if Anoop would like to rejoin, since there's actually still a Anoop session that we're having all these discussions.
Oh, sure. Yeah, I mean, there are things where I think ChatGPT and all other things get astonishingly better results than maybe second graders. I have seen examples where the second grader didn't get correct. ChatGPT got it right. So there is some things going on which we don't really yet understand. But then the point I think I wanted to make is that we should always take it with a grain of salt, the answers that it produces, and it need not be correct all the time. And there is still a long way to go. And like Ben was mentioning, I think transformers have an enormous, and it's a good computation platform to solve a lot of problems. But I agree that it might not be the right, or it might not take us to AGI. Maybe there is something more important that is to be added there. Yep.
Thank you. Thank you so much, Anup, for your excellent and insightful speech.
Thank you so much.